Load. So I starred numbers 3, 6, and 7 as the vector field problems that you should have a look at, because these are the kind of problems that, you know, like I'll put something simpler on a test, but you know, if you can handle stuff like this, then you can pretty much handle anything that I can throw at you. If you could dodge a wrench, you can dodge a ball. So let's take a look at number 3. And we're working with this lattice of points, and you know, there's only 9 points there, but that's quite enough, because it really starts to add up when you go through this process. So I'm going to list all the points and what they correspond to in terms of the vector field. All right, so start off, and really, as long as you have some sort of scheme as to how you list these points, it's fine no matter how you do it. All right, but -1 for most of us will be the first value you come up with. Then whether you choose to go up the line or over, it's up to you. I'll go up the line. -1, 0, -1, 1, then 0, -1, 0, 0, and 0, 1. So just write 3 zeros and then 3 ones, because this is just a copy paste job now. All right, so these points I'm just writing as the coordinates of the lattice. All right, those red points that I plotted on the vector field, or at least the vector field plot. Now what I need from this is -x, -y as a set of coordinate vectors. All right, so that's what I'm going to do here, is I'm just going to negate each part. All right, and by doing that, it's going to reverse all the signs. All right, but since this is typically the kind of thing that I end up screwing up, I'm going to put the brackets in first and then go through the process of negating. Also the commas. All right, so I'll get the commas in, might as well. So all these negatives go away. 0 remains 0. All these positives become negative. Then the trio of values, -1, 0, and 1, are going to get reversed. So negatives become positive, positive becomes negative. And so at the appropriate coordinates, we're going to plot these vectors. All right, so at -1, -1, we're going to plot the vector corresponding with 1, 1. All right, so still copy pasting, but you know, it's maybe a little bit easier to kind of visualize now that we have you know, all the information in front of us. All right, at least that's the plan. So at -1, 1, again, I'm going to plot 1. Let me get a different color, something that'll stand out here. I'm going to plot 1, 1, which is this vector here. Slide it on over. And that would be our first vector. All right. At -1, 0, I'm plotting the vector corresponding with 1, 0. I got to zoom in even though I don't want to have to do it every time. But at -1, 1, I'm plotting 1, -1. So 1, -1 would be this vector. I think I got to zoom in a lot more. right. At 0, -1, I'm plotting 0, 1. I'll do it kind of alongside of it. Here's 0, 1. Zero, 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 so that's easy enough. 0, 1 is 0, -1, but you start getting a sense of a trend here. It seems like everything is pointing at the origin. So once you get an idea of that, then it's pretty easy to go the rest of the way. But if you're not sure, just keep going point by point. At 0, 1, it's 0, -1. So 0, 1, here's 0, -1. We're going to plot that at 0, 1, pointing towards the center again. Right, pointing towards 0, 0. At 1, -1, we're plotting -1, 1. All right. So -1, 1 would be going in this direction. So something like that. But when you slide it down, that's going to put it as a vector aiming for the origin. So once you realize all that, then you can just kind of finish the job. And you end up something like the British flag kind of, Union Jack. So anyway, that's it's pretty easy to do, but only because the values that you're working with are pretty friendly. All right. So numbers 6 and 7, you can see they're along the same lines in terms of level of difficulty. So we still have the same lattice. So I'm going to snag these. But this time we have -y(x) and -y and +y (-x). All right. So we're negating the y and reversing it with the x. Now we already have a list of values corresponding with -y. So I'm going to steal those. All right. Here's my -y set of values. And we also have a set of values corresponding with a positive x. That's right here. I'm going to steal those too. So you find little ways to trim down the work. All right, now all I have to do is put my brackets in and the commas. And I have my set of vectors. All right. So now at -1, 1, I'm plotting 1, -1. All right. So 1, -1 would be this vector. But I'm doing that at -1, -1. At -1, 0, I'm plotting 0, -1. So here's 0, -1. That's going over here. At -1, 1, I'm plotting -1, -1. So here's -1, -1. I'm sliding that up. All right. And if you don't see the circular movement yet, you will, because what's happening is it's following a progression where it's working its way around in a circle in this direction here. All right. But like I said, you may not see it just yet. All right. So the next one is the coordinate -0, -1, which has a vector of 1, 0. That one, that's my big bugaboo. I got to zoom into that. All right, 0, 0 is 0, 0, so we don't have to plot anything there. If you want to plot a point, that's fine. But if it's the 0 vector, there really isn't anything there because it's a vector with length 0. All right, so You can, if you want, just as an indicator that you plotted a point, or you at least considered it, you just put a point there, but you really don't have to put anything there. All right, at 0, 1, we have -1, 0. So here's -1, 0. That's happening in 0, 1. I don't know what I just said. All right. At 1, 1, we have 1, -1. I said that backwards. At 1, -1, we have 1, 1. All right, so here's 1, 1. Comes down here. At 1, 0, we have 0, 1. 0, 1 would be pointing up 1 unit. And at 1, 1, we have -1, 1, which is going to give us this. All right, so you can see the vectors are pointing in a circular path. All right, so if you have, I kind of equate it to a slope field in the sense that if you drop a pebble into this vector field, which represents, the movement of a function, in this case, it's talking about the gradient, right? But it's talking about slope, rates of change, but in terms of both X and Y, then you're dealing with, some sort of movement in that effect. So when you consider it that way, kind of look at it as like a pond, or in this case, it'd be kind of like a drain or toilet bowl you just flushed. And so you drop a little pebble in there. I don't want to make it graphic or anything, but you drop a little something in there and it's swirling around, like what path would it follow? These are the vectors, tangent vectors that you expect to have. All right. So the last one, if it seems like I'm beating this to death, it's a question on the test. So I want to make sure everybody's good to go on this. But I also wanted to show you like the nifty workarounds to keep from having to like reinvent the wheel every time. All right. So the last one here, again, we're working off of our lattice of points. So you definitely want to have these points available to you, because I'm gonna, on the test, I'm gonna ask you to create a vector field using the same lattice of points. I'm not gonna mix that up and say like, oh, we'll do it from -5 to -3 or anything like that. It's gonna be the same lattice of points. All right. So this is y -x. So I'd steal my y values. I could have taken them from anywhere, I guess. And the corresponding values associated with y would be -x, which I can grab from up here. If I were a student, I'd be looking to get an annotation app just for this one problem. Like if I made it through the whole semester doing everything out with pencil paper, I'd be like, you know what? Enough's enough. I need some copy paste options here. Every time. Robocall. How I hate. All right, so these are the vectors I'll be looking to plot, but you get enough experience, you start realizing, oh, okay, so I can just kind of play this out in my mind. At -1, -1, you're plotting a vector corresponding with -1, +1. All right, so -1, +1 would be that movement, but I do have to zoom in because you just see what I'm up against here. 0, 1 is what I would plot at -1, 0. So that's this. But then once you get the idea of what's happening, like, wait a minute, this feels awfully familiar. Then you start realizing, oh, wait, I can kind of rely on stuff that I've already done, because this seems like it's the exact opposite of what we did over in the previous one. All right. At negative 1, 1, I'm plotting 1, 1. Dang it, come on. At 0, 1, I'm plotting. I already lost it. Wait, where am I? Oh, I'm sorry, I'm at 0, negative 1. All right, 0, negative 1, I'm plotting negative 1, 0. So that's this guy. 0, 0 is 0, 0. Put a little placeholder in there. 0, 1 gives me the 1, 0. All right. At 1, negative 1, I got the negative 1, negative 1. So that's this guy over here. Zero, negative 1 is at 1, 0. And 1, 1 gives us 1, negative 1. So that's this guy over here. So it's given that same circular path, except going in the clockwise direction as opposed to counterclockwise direction. All right. So if you follow any kind of transformations that we've been talking about in the last part of the unit, where we're talking about matrix multiplication for transformation purposes, you might remember that a 90-degree rotation around the origin in a counterclockwise direction was represented by negative yx. All right. So if you wanted to go clockwise, it would be y negative x. All right. So and it equates to a reflection in over the line y equals 0 and also x equals 0. All right. So anyway, so that's plotting vector fields. These ones in the middle, honestly, I'd love it if we had time to plot them, but really, if you kind of think about what's happening, is it's really just going to give us similar plots to what we already have, except guaranteeing that you're dealing with unit vectors. All right. So if you divide it, because the square root of x squared plus y squared is the magnitude of the given vectors. Now, each of these vectors have magnitudes of 1. All right. So we would be dividing each of these vectors by a 1. So you would actually come up with the same vector field. And that would be true for the next one also, because each of those vectors have a magnitude of 1. So there's really no work to be done. But you know, to expand upon that, you would ask, well, what if we had a vector whose magnitude wasn't a 1? All right. And actually, that's not true. Let me get rid of this for a second. It is true that it would be magnitudes of 1, but some of these actually don't have magnitude. So they'd be shortened up a little bit, because the ones where the x and y components, they actually have a magnitude of radical 2. So if you want them to have magnitude of 1, you'd have to shorten it up to, it would be about 0.7-ish. So it would really be, they'll just do a quick sketch. But like I said, I'd never ask you to do this by hand. It's too much trouble. All right. So this one's a little on the long side. So let me just kind of, oh, now it's on the short side. I'm just going to get free-handed again. All right. So these vectors, I would shrink them down so that they're about 7/10 of what they were. All right. So it'd be something like this. Because the idea is that its magnitude needs to be equal to 1. But what's going to happen is, in order for that to be the case, if this is going to be a magnitude of 1, then each of these has to be radical 2. Actually, no, that would make it 2. Radical 2 over 2. I don't think I can make my writing any smaller. Or I'll write it as 1 over radical 2. Maybe it'll be less. No, it's just terrible. I'm going to make it as skinny as possible. All right, and so that would give you the magnitude of 1, but that would be the computations that you would need to do in order to get there. All right, not something that I would make you do by hand, because again, we're only focused on the lattice of points that are between -1 for x and +1 for x, and same domain for y. All right, we're ignoring everything in between the integer values. There's a lot of stuff we're ignoring. All right, so to go crazy about stuff like this would be a little bit beyond what we need. But it's really just kind of like getting at the idea that we're dividing by the magnitude of each vector, creating unit vectors. All right, but there's other things that can be done. We can divide. I mean, if we wanted to, we divide everything by 2. You know, so there's a whole slew of possibilities for vector fields. All right, so now I kind of feel compelled to do the last one, or at least kind of chuck in the solution. So it's like, you're right there, dude, might as well. So all these diagonal ones would be shrunken down a little bit. All right, and that middle, you know, I might as well just do it here, but it would be about something along these lines. So the ones on the axes would go all the way in, but the ones that are in space wouldn't quite make it. And so like I said, not going to make it to that one. So it'll be something simple along the lines of what you see here. But I even mentioned last class that I'd give you one of the components as a constant. So expect something along the lines a little bit like a hybrid between numbers 1 and 2. So like what you saw in the practice test, and you see something like 1, y, or 1, -y, or 1, 2y, or something like that. Or maybe the constant will be the y, and maybe you'll have like 1/2 x, 1, you know, something along those lines. Try to keep it simple. Because I don't want you to spend the whole test making a vector field and spend way too much time on something that could be generated by technology. All right, so let me stop that recording.